All right, it is 1:05. We're ready to start the lightning talks. I apologize in advance for any mispronunciations of companies or people. I think all the names are pretty straightforward this time. All right, so our first talk is Lance Bissaw of Applied Research Associates.
All right, thank you. Can you guys hear me in the back? All right, excellent. As he said, Lance Bissaw, Applied Research Associates. I lead an AI and data analytics group out of ARA. Excited to talk today about some of our, oops, it's the clicker. So a little bit of background about ARA, if you're not familiar with us. 40-plus-year-old company, about 2,000 employees, $600 million in FY23. So, you know, not a mom and pop shop, but not a huge business either. So we're kind of in that, we kind of play that middle role. You see in the map, we have offices all around the country. One of the most important things that we like to talk about what we do is we do work that we're passionate about. So that kind of goes way back to the founding of the company. Across the right-hand side here, you see kind of a broad overview of some of the areas we work in: national security, infrastructure, energy and the environment, and health solutions. I will say most of the work we do is in national security. So we're primarily a DoD and IC contractor. Next slide. So to get in a little bit, obviously in 5 minutes, we don't have a lot of time to talk about experience and expertise, but we do have a very deep bench of developers that work in a lot of these areas, very, very relevant to Lynx. C4ISR systems, of course, AI and ML, robotics and unmanned systems. Specifically, our group does a lot of work in 3D reasoning, we like to call it. So from ground level imagery, low flying UAVs, security cameras, taking that information, taking that data, extracting information, and then reasoning about the geolocation of things in that imagery, as well as the original sources of those imagery. So we do have more than 10 years of working with IARPA. So across the right here are some of the programs we've worked in the past. ACES, Finder, Lego, and SMART. SMART is ongoing. Again, one of the biggest ones was the Finder ones that really kind of jumped us off with this geolocation problem. So we have had a lot of spin-out technologies related to this capability. We've done work with GPS-denied geolocation for the Army. We have a lot of capabilities of extracting meaning, extracting information from ground-level photographs and geolocating them. Critical to all of these projects has been our collaboration with partners. We're really looking for academic partners and other businesses to bring in, make a strong team. When we do these types of opportunities, you know, it's very collaborative, right? We brainstorm together, we come up with solutions together. We don't just bolt on an academic for the purposes of including them. We really sort of bring them into the kitchen, if you will, and build a solution together. In addition, we have a lot of experience taking these technologies and transitioning them. So right now, Finder capabilities have been transitioned and are operational in the IC. As is our solution for the Lego problem as well. Already running short on time here, but a little bit about some of these capabilities. Already kind of hit some of these at the high level. We do a lot with automated target recognition, so few-shot learning, even zero-shot learning. Again, a lot of our work comes out of understanding the 3D environment. So we have a geospatial aware ATR solution, as well as traditional machine learning solutions. Quick down there on the bottom left, right? We've worked with lots of different sensor modalities, as I've kind of already touched on. On the top right, we've already done similar work with this, where we have registered different sources of imagery with respect to a model or with respect to a sort of a common reference frame. We've also done, again, through the transition of some of the data ops, or the IARPA data ops. So, you know, we want to partner with again, academics and other industries to build this solution where we let those academics and let some of these other businesses kind of develop those core nuggets, those algorithm golden nuggets, we like to call them. And we worry about the test and evaluation. We worry about the contracting, and we worry about the systems integration. So in the quick 20 seconds I have left, sort of already said some of this. We are planning to prime. I'll be around all afternoon. Please come and introduce yourself. Look forward to hearing more about what you guys can do and how we can work together. And that's it.
Our next speaker is Colin Adams of IARPA.
Yep, you nailed it. All right. My name's Colin Adams. I work for Arate. We're a small business of about 350 people. We have sites all across the country. And if you want to get in contact, here's the information at the bottom. So a little bit about Arate. We are an employee-owned small company, and we really focus on and excel at kind of the remote sensing and the detecting weak signals for intelligence applications. So heavily cluttered environments, extracting extremely low SNR signals and providing useful information to mostly government customers, DoD, IC, and we also kind of really pride ourselves on a low false alarm rate. And so I'm going to go over some previous work that we did that's extremely relevant to video links. It was a series of SBIRs sponsored by NGA under NGA research. And basically the problem that we were asked to solve was, okay, how can you comprehend systems of unknown traffic camera streams with extremely little metadata assumed? And all of the results were performed on real traffic camera streams. There's no simulation. This is all data that we have and got from the real world. And so that's another big selling point. I think we already have lots of video data in hand for further algorithm development. We have literally terabytes of data. And we've done previous work on re-ID of both people and vehicles, and you can kind of see it at this archive paper. And so kind of the highlight results I wanted to share was there's kind of two con-ops that we were going in to trying to solve. The first is like, can you get a quick estimate of a camera, its geolocation, just like, what neighborhood is it in? And it's kind of our median offset error, depending on a few assumptions, was anywhere between 100 meters and 450 meters. And the second con-op was, okay, what amount of road length will you have to search to find the exact camera location? So the little quip that we say is, what trash can is the camera looking at? That's the level of precision you need. And so we would find 50% of the cameras in anywhere between 1/100% of the possible road space that you need to search to 0.5%. And the most probable road that, where we think this camera is geolocated was correct anywhere between 10 to 25% of the time. So we say you need to look at that road and you'll find the camera, up to a quarter of the time, that's the right road before you move on to the next most likely road. And so here's a little map. That's where the true camera is located. And it's a cute little result because when we downloaded the data, it actually, we knew where ground truth was. The reported camera location was here. And if you follow, this road, like as the crow drives, I guess, it's about 2 miles apart. And so, when you look at the recorded footage and compared it to Google Maps, there's this chevron, which shows, where, the map actually is. So the point is, we've thought hard about a very similar problem. We have a good idea of kind of the important pieces of the problem that are solved and need to be solved, especially for this phase 2, where we start to re-identify vehicles. And yeah, that's kind of all I'd like to say. We would love to discuss teaming. You can contact either Tim or myself, or come talk to me after this. And yeah, all I have. Thank you.
Next up is Naresh Kuntur of Halo. Okay.
Hello, everybody. My name is Naresh Kuntur. I'm with Blue Halo. And let me see if I can advance this slide. There we go. So Blue Halo was purpose-built to serve national security needs by combining several small business companies. And we were formerly a small business. And now we are at Blue Halo over 1,500 people spread across several parts of the country, 3 main locations in the DC area, Albuquerque, and Huntsville, Alabama. Most of the people relevant to this group and project are in Rockville, Maryland. And we are in the AI/ML Center of Excellence, where we work with lots of computer vision projects, NLP, LLMs, text kinds of projects, and multimodal, multi-sensor projects. In the AI/ML and related divisions, we are about 50 to 100 people at this point. And Blue Halo works across 4 main thrust areas, as you see in here. And the AI/ML division will lead this effort. Relevant to this project, so we have several IARPA projects that are ongoing, 5 active ones, and I've listed 3 of them here. So SMART is currently in phase 3, and on RIVA, we are doing novel view rendering with varying altitude images, where we take images from multiple viewpoints and stitch them into essentially do NERF and render novel views. Sintra, that is a space domain awareness project, where we are monitoring space object debris, and there is computer vision involved, as you would imagine, looking through a telescope kinds of images. We have done a fair bit of RE-ID related research in the past few years, and I have listed 3 of them here. So one was an effort that we did with DARPA, where we looked at a multi-sensor, multi-camera detection and tracking problem. And so there, RE-ID was a core piece of how we build up what cars look like from different places in a city. And we were doing detection and tracking with not just video, but also combining audio, which is not relevant to this, but the goal was to take multiple sensors and do detection and tracking. As part of the DEL-DOT traffic monitoring, prediction analysis capability software of tools, that we work with the state of Delaware, their DOT, where they have given us access to their entire camera network, and not just their cameras, but their sensors, like the inductive loop sensors that they have below the ground. And we take that and do traffic flow analysis, monitoring, prediction of when things go wrong, and so on. I do not know if we can use that data for this project, but if we can, that's a fantastic source of data. But as part of that, we have developed RE-ID algorithms to detect vehicles from different camera view angles, for example. And we can also control where we placed some of their mobile camera units. And so we've been working on that for a number of years now. As part of an MDA project, that's Missile Defense Agency, we have developed data association and tracking algorithms for things flying through the sky or space and doing various kinds of maneuvers. Though the data is very different, the core technology in terms of the algorithms we develop, I think will be relevant here. We do all of this in collaboration with academic partners and other companies, and we work across a number of universities on IARPA projects and NGA and AFRL projects as well. So we would love to team with you if you're interested in talking to us. I'll also point to one other area of research in geolocalization. We have been working with NGA, which is a follow-on to the Finder program. And so as part of Glimpse, we developed some capability, and we're taking that to the next level to build a geospatial foundation model. And I will stop there. Please reach out. And here is my email at the bottom. Thank you.
Yeah. Hi, everyone. My name is Rodolfo Valiente. I'm a research scientist at HRO. I'm very excited today to present our lightning talk. So just as a quick intro to HRL, we are a limited liability company that have several locations across Southern California, including Malibu, Camarillo, Thousand Oaks. We are jointly owned by two members, General Motors and Boeing Company. And our core competency is rooted in our our core competence is rooted in the cutting edge research infrastructure that we have across our 5 different laboratories: Intelligent System Lab, Sensor and Electronics, Microfabrication and Technology, Materials and Science, and Vision Systems. That allows us to do this cross-laboratory research. We have an excellent track of innovation record with more than 1,700 patents that are issued in the last 20 years. Mainly for us, the revenue from government contracts made up more than 70% of our research. Just as a quick view of our facilities, we have our main headquarters in Malibu. That is like a big facility by the Pacific Ocean. Our latest facility is Westlake. In the last years, so we have grown significantly, and then we have around 1,000 people now spread across these different labs, with more than 90% holding advanced degrees. Yeah, so yeah, I think this was not the last slides, but yeah, I can go through. Yeah, so I think we send updated the slides after, but yeah, it's okay. Yeah, so mainly there is some image and small graphics there, but mainly I'm part of the Intelligent System Lab. That the main mission of our lab is develop robust intelligent systems that are proficient, adaptable, scalable, and trustable. And we spread our work across four technology centers shown here on the right. The first technology center is knowledge navigation, and it aims to provide timely decisions by analyzing complex multidimensional data from across different sensors. The main focus is in graph computing, causal reasoning, explainable decision making, and computer vision. So we have the Proficient Autonomy Center, that the focus of the center is in develop improve, enhance intelligent system, focusing mainly on data efficient continual learning, human-like reasoning, and metacognition machines. Then we have the Operational Autonomy Center that is focused on trust and make AI systems reliable in mainly critical domains. And the main focus areas for research is assured autonomy, adversarial AI, and scalable AI, also system integration and AI engineering. Finally, we have the Augmented Intelligence Center that have focused in improving communication between humans and machines. The research there is bidirectional communication, cognitive model, human state modeling, also data collection, and we do a lot of human research, human subject research on that center. So across the different centers, we have a lot of competencies that are relevant to the video link programs, and I will highlight the main ones that we think that are most relevant for partnership in the program. Mainly during the last 10 years, we have worked in several computer vision and machine learning projects with a lot of capabilities in threat detection, object detection, forensic analysis, tracking, anomaly detections, and continual learning. And the main constraint then was that working with limited label data and in an open world setting, which is very relevant for what we are looking in links. And I will highlight a few of the programs that we think are more relevant for here. Yeah, mainly because the time constraint. So we have the DARPA CT2WS program that was focusing in threat detection in wide field video using bioinspiring processing, so mainly focusing on efficient and bioinspired computing there. And then the ONR Nemesis program that was about low swap real-time surveillance from drones and multiple drones for 3D identification. Across these two programs, we developed capabilities that are very valuable for object tracking across different for the case of the drone, across different drones. And then we have the LWL program when we focus on advanced deep learning methods that can learn with few labels. And the main capabilities that we developed there that is valuable for links is related to the zero-shot object detection and identification without having a prior knowledge about the objects. Finally, a more recent program as well, we have the MMA program that it was about knowledge graph analytics for connecting the dots and finding the needle in the haystack. And during that program, we developed capability for multi-fusion data analysis using diverse source of data. Yeah, so yeah, thank you very much. We are looking for potential collaborators in across the different areas.
All right. Hello, everybody. My name is Scott McCluskey from Kiteware. I'm here with Anthony Hoogs, who's in the red shirt back there in person, and Keith Fieldhouse is on the online platform if there are people there that want to send him some questions. I'm here representing the Kiteware computer vision team. So Kiteware is an open source software R&D company. We're based here in the US with several different offices in Albany, Chapel Hill, Arlington. I'm from Minneapolis, and we also have a French subsidiary. We at Kiteware are divided into 5 different technical groups, which you see in these hexagonal shapes around the middle. The work on this program is most related to the computer vision group. The computer vision group is the largest of these groups. You can see some of the open source toolkits in the upper arc here. We do funded R&D services primarily by the US government with customers like IARPA, DARPA, and others. We are not a company that's in the business of collecting intellectual property, being an open source company. So we have a lot closer to 0 patents, I think, over the last 20 years than my predecessor here at the podium. We deliver software developed on these programs with unlimited rights to the government. And when permitted, we do these as open source, which is generally the case with IARPA. So in terms of video links related capability, we've been doing a lot of work over a number of programs for person re-identification, both with and without clothing changes. We also have some past work in vehicle re-ID. The 2 most relevant, most recent programs for the person re-ID work are the DARPA URSA program, which recently concluded, and the ongoing IARPA Breyer program, where Kiteware is priming an effort. This video you should see on the right is a video from a data collection that we performed under the Breyer program. It's a fairly large scale as these things go, about 250 people. One of the issues on Breyer that may come up here on video links is that the government data that will be evaluated on may or may not have restrictions about using the data in publications. So when we collected our data set for Breyer, we made a point of asking the participants to consent, and they all did, to use their likeness in technical publications to support contributing back to the scientific community. There's some other statistics here in addition to the video where you see these cameras mounted on a crane. There were a number of cameras also indoors and everything else. So all of that is to say we have a lot of experience with IRB and privacy compliant ground truth video collection and annotation. You also saw some Kiteware data earlier today in the program overview talk from the DIVA program. And so that's a core capability that we do very well. Again, TA1, we do a lot of work with person re-identification. With respect to TA2, we do a lot of geometric camera solutions to figure out where people are in the scene, occlusions, these sorts of things, and a lot of fundamental research on open set recognition, anomaly detection, low shot learning through participation in DARPA programs like Sail-On and Learning with Less Labeling. We routinely lead large programs for IARPA and DARPA with multiple university participants, and as is the case on Breyer, we try our best to insulate the university contributors from the gory details of the API and let them focus on research. So with that, I'll say that we are planning to prime a proposal team here. We're looking for partners with expertise in the items listed here. So vehicle re-identification, instance level recognition for generic object categories within TA1, but within TA2, security camera network mapping, image and video geolocalization, and then just sort of generally pre-training and distilling for multimodal video models. And if there's anybody who has an approach that can help us do more effective data collections to support the research, we'd be open to hearing about that. When we run these teams, we participate collaboratively with the Kiteware team. Being an open source software company makes it very easy to share details, share code with everybody, have everybody running the same system without any IP related firewalls. As I mentioned, we deliver software with unlimited rights to the government, and we prefer people on our team to do likewise. So again, you can find me during the day or Anthony back in the back of the room in red.
All right, perfect. I didn't expect to actually see it up here. So I'm Derek Walbert and Will Rohr here, representing L3Harris. Next slide. So kind of the obligatory overview. So L3 Harris, about 50,000 people worldwide, divided up into 4 different segments there. We're representing the Space and Airborne Systems segment. And then the kind of smaller business area in there, Autonomous Intelligence Solutions, so AIS. And kind of the bread and butter that unites everything there in AIS historically has been the study of the imaging chain. So we have quite a few imaging scientists. I'm an imaging scientist by trade. And really just the study end-to-end of imaging chain, the modeling and simulation of the imaging chain. And like pretty much everybody here probably had to adapt to AlexNet, right? Deep learning taking off. So of course, where that fits into the imaging chain all the way through there. And here, of course, hitting a lot of the back end. So data and decision processing. You can see some of our core capabilities there as well that kind of hit some of those things. Maybe. I can wave my hands around. I do that a lot. I'm used to the 1 or 2 hour thing, not the 5-minute thing. Good. Okay. Maybe we could get it full screen, maybe not. So just wanted to talk through one example that we have. So while I'm part of AIS, we also, like many folks here, have AI ML groups. One of the things that we've worked on that's pretty representative, we think, of course, we're looking at the detection, tracking, custody, and behavior pipeline. We jumped right to the end, right? We wanted to look at behaviors, and behaviors are difficult, mainly with semantics sometimes, and really trying to understand exactly what folks are going after. So somebody could say, where's this vehicle going? Okay, so now you can answer that. Where's this vehicle going based on a global distribution, based on a local distribution? And as soon as you say, where's this vehicle going based on its previous behavior, re-ID comes in play. So we have done a lot here with re-ID. You can see examples there. What's hidden, unfortunately, a little bit here, we can also come in and we can generalize, right? You can just go grab random images there right off of Google and say, hey, we've seen this before. We can do that on a daily scale. We have months and months and months of data. And maybe now is a good time to pause and just say, yes, we have invested in kind of our own systems to go get some of this data at ground level. We also work with university to go and collect from different collection geometries. We have multimodal data. The thing that most people miss, and it's kind of difficult when you go and get data, is recurrence. So that's our big piece here. And we think that that's likely to be useful here for what we're doing with video links. On the bottom right, of course, this is just same modality, but looking multi-camera, so doing a complete chain of custody just with re-ID itself. Next slide. So there's kind of 2 caveats on the next slide once that comes up there. Okay. The first one is, yeah, slides were prepared maybe before we had all the information here. So you'd probably see quite a bit more on some of our photogrammetric expertise and multi-view geometry, structure for motion, everything that we've done in the past there with geo-rectification. But maybe a kind of roundabout story. Yes, offering strengths in re-ID and behavioral analysis. We view that as a spectrum. When you have a ton of pixels, when you get all the way down to just 1 pixel, how do you start to do re-ID? You have no image information. And so certainly looking at re-ID across all of that. But the roundabout here, just kind of the next one's playing. We also have done some things with developing state-of-the-art architectures for just trying to have a all-purpose registration technique or stabilization technique. Again, very much like what's at play here. At the end of the day, you still have to go find features and build up math models so that you can do some of these things, right? Even if it's a GFM kind of approach there. So yeah, we a lot of expertise in deep learning for sure. That's where we've been spending most of our time, probably too much time, and need to get physics back in here at some point. And then just showing some work that we had with masked autoencoders and you know, trying to come up with our own kind of generalized feature extractors towards that end. The second caveat with my last 10 seconds here, seeking partnerships in fusion and tracking. But again, given that these slides were prepared a little bit earlier, yes, we do have expertise in the geo-rectification, geo-localization arena. But there is not one all-purpose fusion technique or tracking technique or geolocalization technique. So certainly looking for help there. love to partner. Please come talk to us.
Okay, good afternoon, everyone. So this is Xiangming Liu from Michigan State University. I'm going to share some of our work relevant to this program. We're best known for our work in terms of biometrics. So on face area, we started to work on this about 2001, and right now we're prime in the another project, which is Bright, interested in doing people recognition at a far distance, as far as about 500 meters, 600 meters. We're also working on body as well as gait. In terms of object detection, we do both 2D as well as 3D object detection. I think 3D object detection is quite important for the tier 2 of this project. And for 3D modeling, object modeling, as well as doing NERF, this is important for generate different view of the same object in order to matching two different same object on the two different view angles. So in the rest of time, I try to pick up some of the highlights in these research areas. So for face area, I know this project is not necessarily found in face research, but our experience in the Bright project shows that even when the face is as small as 15 by 15 pixel, you can still do some sort of recognition. Not necessarily recognize who he is, but at least for the soft biometrics, demographics, age, as well as gender, you can still recognize. So we think this might be still helpful for this project. Now, in terms of personal ID, one of the key problems we're trying to study is that when you have clothes changes, let's say from today until tomorrow, right? When people wear different clothes, how can you match in two images of human bodies? We think the most useful information is trying to reconstruct 3D body, naked body shapes. If you can do that, then you can, based on the body shape, to do the matching. This essentially is what this approach is trying to do, which we do analyze by sensor approach, starting with a single image, try to decompose into different parts, including the body shape, the clothing, as well as the color information. And then even without ground truth 3D shapes, we can actually reconstruct two body shapes, giving any single image, as you can see on the right-hand side. One, we can reconstruct naked body, which is for matching purpose. Second, we can also reconstruct closer body shapes. So in addition to that, recently we're also working on using large models such as clip model for doing people matching, because clip model has a lot of domain knowledge. This is especially useful when you have a language description about the body shape. For example, this person is petty, this person is muscleish. This kind of description can actually be incorporated in the learning process. Because of that, eventually you can have a better essentially matching system between two people. Again, this focuses on mostly on phase 2 of the project, which you have changing clothing of the person real ID problem. And next, we also work quite a bit on perception problems, especially on 3D object detection, though this is mostly driven by the autonomous driving applications. In this case, you can see that we're detecting object in 3D space. That's why we have 3D cubic. We track them over time. That's why on the right-hand side, you see the bird eye view location of the objects. We also have this history as well as forecasting into the futures. So everything is done in the 3D space. We even eventually have a velocity estimation in terms of mile per hour for every moving object as well as a home vehicle. So we think this is important for the tier 2 of the project because you want to have a precise estimation in terms of distance of the object to the cameras. And from the Q&A session, we learned that in this project, intrinsic of the camera is not being provided from phase 1 to phase 3. So therefore, for different camera types, sensor types, knowing the intrinsic is very important. Typically, you do this from the checkboard, right? It's a very classical method. But in this work in Europe last year, we published that giving a single photo without any other information, no checkboard, we can estimate intrinsics. So this will be essential for doing the inverse projection to estimate the depths of the object. Especially we want to build a universal depth estimation, which will be essential for, estimate the distance to a chair, to a bag, for example. By the way, this is the Dolly sequence. It's a very classical technique in movie shooting sequences. The ground truth kind of the intrinsic is kind of monotonically increasing, but we don't have the ground truth. But at estimate 1 at least is also monotonically decreasing, as you can see from this sequence. Finally, a lot of challenge in this project is also has to do with open set recognition problems. So here we show that using large language models, you can actually understand object even without the training data. So we show that if you're giving a cat and a lion by using language description, by using ChatGPT, you can actually figure out what are the difference among these two relevant objects. And through that, we can do zero-shot object recognition. I think this will be useful for going to phase 3 when we want to do sort of generic object real ID problems. So finally, in summary, we are quite experienced in terms of biometrics, but we also have a wide range of other computer vision expertise from object detection to 3D vision task, as well as object modeling across different views. So we are mostly will be joining the project hopefully as sort of a sub. So whoever interested, welcome to talk. Thanks.
Okay, great. My name is Eric Vega. I'm representing Michigan Tech Research Institute. Next slide.
There's a clicker.
Oh, there's a clicker. Perfect. So we are a research department of Michigan Technological University, but we're actually located in Ann Arbor, Michigan, just a few minutes away from the University of Michigan engineering campus. That's kind of the brochure materials. We are kind of unique as a research organization in that even though we're affiliated with the university, we have our own facilities. We get all of our own funding. None of it comes from the university. And we also have closed facilities that support classified research with a good portion of our staff having clearances. Much of our work is with DoDs, but we also work with civilian agencies, primarily, I would say, closer to fundamental research. So sensor characterization, mathematics, fundamental statistics applied to practical problems. Yeah, so our breakdown is primarily PhDs and masters, so higher degree retainers. We've recently hired a lot of mathematicians. That's my background on mathematics. My colleague, Meryl Spencer here is a physicist. In terms of what we offer, oftentimes we're coming in as subcontractors to the prime contractors, providing assistance in terms of fundamental research. We are much smaller than many of you, so $12 to $15 million a year, with a PI-driven model that basically says that we only eat whatever contracts we're able to capture ourselves. Our major sponsors: DARPA, NASA, AFRL, and as well as many of the big primes. So this kind of gives a snapshot into some of the imaging work that we've done in the past. So we've done a fair bit of work on optical system characterization, which you can think of as maybe learning the transfer function of an optical system. If you're able to do that, you're able to do things like image restoration or super resolution imaging, kind of from the physics based perspective. And we also do a fair bit of work on characterizing information theoretic bounds of estimation problems. So in other words, saying how well could you do this problem in the best case scenario, given the let's say noise characteristics. So in terms of related work, we have done work with DARPA and IARPA. I think somebody mentioned the Core 3D project, so we were involved with that as well. Also the URSA project. We've done work with real-time processing of video imagery from drones. So this is one where we've got a couple of fisheye cameras mounted on that drone that we were de-warping and processing in real time as the drone was doing its whatever it needed to do. We've done work for so we were a finalist on the DARPA Subterranean Challenge, which was this kind of swarming problem for robotics. Meryl was one of the lead engineers on that, and the relevance to that problem, to this effort, is the sensor fusion from high-level track data across heterogeneous sensors. And then we've got some additional work on long time scale target characterization. So yeah, in terms of what we believe we can offer is we're an academic partner, so we also generally don't have very strong attachments to being able to release our code. So we're always happy to do that, and because we're often in the sub role, we're pretty confident in being able to integrate into these sort of greater systems that have additional complexities that maybe we are not necessarily responsible for. But that's it, yeah. So Eric Vega and Meryl Spencer, reach out to us if you're interested in teaming. Thank you.
I'm Nigel Mathis. I'm the CTO of AI at Morse Corp, which means that if it sounds like AI, I probably work on it at Morse. But I was going to give you guys a company overview of who we are and what we do. We're a small business located in Cambridge, Massachusetts, founded in 2014. We've got about 170 employees now. This is the plus there. Plenty of interns and co-ops. But some key aspects of our business model is that we're 100% employee owned, and we deliver all technologies with unlimited government data rights when we do this research. We're predominantly technical staff, very little overhead. We just like to get the research done. I'll dive right into capabilities that are relevant for video links because I think Morse's core competencies lie in how we got started with AI work, and it's computer vision. A lot of our work started with detection, tracking, localization of both imagery and video data. And nowadays we're prime on one of the DoD's largest computer vision R&D programs. A lot of the things we like to do are develop new state-of-the-art algorithms for localization. One of the projects we also work on is aerial localization of an autonomously flying parachute platform. And some of the relevance to video links in that regard is processing video that is of questionable quality in real time and being able to derive based upon landmark recognition position in the sky. We do the opposite also, transforming what we see on the ground into geolocated coordinates. Some of the other work we do is related to deploying some of the more advanced deep learning based computer vision algorithms for various applications. And that includes both object detectors, segmenters, and nowadays open vocabulary object detection is another big research part we're getting into it currently. We do a lot of work developing for disparate sensors, as I indicated. And nowadays, we also are getting more and more into self-supervised, unsupervised embedding analysis that might be relevant for doing target re-ID. Another key focus I want to highlight is, I say, optimizing data sets and labels here. We do a lot of work, not just to figure out how models can be trained best, but how the data can serve these models better. And so we do a lot of analysis internally on both training, testing, data sets for video and imagery that I believe definitely will become relevant in this program. I'll highlight too, some of the things you can Google. So if you go to inquisit.ai, there's a toolkit that Morse has developed that covers the spectrum of how you could analyze computer vision models, test them, measure your data, and then do some extra R&D kind of interesting stuff about metadata augmentation. So for example, if imagery comes with no metadata, we have technologies that can actually create metadata that might be relevant to both image quality characteristics and pose. And so I'll highlight we're looking for teammates. So right now, Morse feels we have a lot of capabilities for the detection, tracking, and localization aspects of these programs, but we'd lack novel data sets where the data is coincident for multiple sensors and time-stamped, labeled in that regard. So any novel data sets and ways to collect data during the program, extremely interested in talking to you. The other side is doing 3D work in terms of developing and measuring and localizing objects in 3D points, whether that be point clouds, whether that be developing voxel grids, whether that be doing other ideas to essentially develop a 3D view of the local space. And then finally, deep academic expertise. We're DoD contractor exclusively, and so any universities that are interested in partnering that bring algorithmic expertise, we're very interested in talking to you as well. If you need to talk to me, I'm here, or you can contact me at the email below too. Thank you.
Hello. Hello, my name is Kemal Labasolu. I'm a principal scientist at Nexepta. So Nexepta is a small business. We are founded by former government and industry research engineers and research scientists. We are headquartered in Gaithersburg, Maryland, and we like to create innovative technologies with high impact operational transition and commercialization. We have core areas that we are interested in. These are AI/ML applications in computer vision, NLP, and radar signal processing. Related to this effort, we have a lot of computer vision work that we did in the past, and also generative AI for data augmentation part. This is a little bit more like a Venn diagram of our core technology areas. We have AI/ML, data analytics, cybersecurity, next-gen communication and spectrum, and in the overlap of these are actually the networks and systems. We have worked on multiple frameworks for computer vision, adversarial machine learning, synthetic data generation, and other signal processing and image processing areas. And related to this one, to this effort, we have a lot of work on object detection with tracking with different sensor modalities. So this would be images captured at different altitudes or point of views. Although this is not of interest, are like infrared-based target detection, ISR-based target detection, and cross-view matching. We have done a lot of work on sensor fusion. These are mostly DoD work. And we have work on multi-target, multi-camera tracking, and identification. So at that point, it sort of divides into a few areas, like with tracking vehicles across multiple cameras, and also pedestrians in different street cameras. So another area that we are strong in is open set recognition, right? Like whenever there's a new target, there's a new object, and image to text retrieval using large language models. So that sort of covers what our related work for the IARPA. We have hands-on experience with data sets for multi-camera traffic cameras and pedestrians across multiple cameras, and developed AI models. So those are, I think, going to be useful in phase 1 and phase 2 and phase 3. So thank you.
Hello, everyone. My name is Jiaden. I'm an associate professor from Department of Computer Science at Princeton University. And here I would like to highlight some capabilities that are relevant to this program. We have a lot of experience in 3D reconstruction. In recent years, we have developed a new approach to 3D vision that we call optimization-inspired neural networks. Basically, it takes the best of both worlds, neural and classical. The ingredients involve recurrent neural networks and differentiable optimization layers. And using this general framework, we have achieved large improvements on many 3D vision tasks, from optical flow, SLAM, to stereo depth, to 6D object pose. For example, we were 30 to 40% better than prior state-of-the-art on the problem of optical flow, which I think would be relevant for tracking generic objects. We generally have a lot of expertise in reconstructing scenes and poses of cameras, as well as any specific objects. We also have a lot of experience in object recognition. I was the first author of ImageNet way back, and I have worked on object detection, human pose, and fine-grained vehicle recognition. And we have another capability that's fairly unique, which is procedural synthetic data. Last year, we presented InfiniGen at CVPR. It is a procedural generator of infinite synthetic data that are rendered by computer graphics. You encourage you to check out our website, and there is a introduction video that showcases the capabilities of the system. In general, this is a generator that takes random seeds and optional user controls and output images and videos that are randomly generated that cover a wide varieties of scenes and objects. And here are some samples. And a defining feature of the system is that it is 100% procedural. So everything is generated from scratch using randomized mathematical rules. This includes shape and texture, material and lighting, arrangement, animation. Because it's 100% procedural, we use no third-party external assets. And everything's interpretable. That's a purely symbolic system. There is no AI, there's no neural network weights. So this means it's very easy to customize for particular applications, and you have full control of the synthetic data. And because it is procedural and based on conventional computer graphics, you can get any kind of automatic labels, from geometry to object labels. You can have 2D boxes, 3D boxes, you can have segmentation, you can have optical flow, you can have surface reflectance properties. I think and by the way, it is free and open source, and it's already very popular on GitHub. Relevant to this program, we think that data can play a very important role. One idea is to use InfiniGen to generate customized, tailored synthetic data. For example, we can have procedural objects like vehicles placed in diverse procedural scenes. We plan to sub, and we're looking for partners who will be prime. And I will be here today and happy to talk. Thank you.
So hi, everyone. I'm Ashley Antonides. I'm here representing 26 Technologies and the AIML group. We have several folks online as well. Just a quick overview of 26. So we're located about an hour and a half from here in Arlington, Virginia. We're about a 600-person company. Majority of our staff are cleared. We do have facilities for supporting classified work in case that comes up in this program. 26 is very R&D focused, so we've supported over 60 R&D focused programs across IARPA, DARPA, and other IC and DoD sponsors, primarily focused on cybersecurity, embedded systems, and information operations. A lot of our AIML and computer vision work falls under the cybersecurity business unit, which I'm in and my group is in, where we do a lot of work on programs like DARPA Guard for ML robustness, including testing models like multi-object trackers and object detection. We also do a lot of work on reverse engineering where OCR and 3D reconstruction comes into play as well. We also have a suite of products that we support, and I mention it primarily here to the extent that we have these products deployed in operational settings, and there is a nice feedback loop with our R&D teams in terms of understanding operational use cases, getting kind of a really on-the-ground set of requirements from our operational users, and then at the end of R&D programs, transitioning that research into operational capabilities. Thinking specifically about the LINKS program and especially about TA1. So again, our team has deep expertise in machine learning, deep learning, computer vision, object detection. We'd be really excited to work on some of techniques for extracting more robust features across different illumination and time of day, different day conditions. We've also done work on synthetic data generation too. So we'll be really interested to work on 2D to 3D reconstruction and some of the synthetic data aspects for the program. And then thinking about TA2, or I guess generally across the program, we do also have folks who also have remote sensing and photogrammetry background. My background is in ML, but also remote sensing, kind of back in the day. Folks who have worked across different phenomenologies as well. So we'd be really interested to work on things like sort of specular independent features, again, sort of illumination challenges from different times of day, and also some of the challenges with moving cameras as well. And then in terms of teaming, I think we're looking for folks who have maybe more expertise in biometrics and some of the temporal aspects of the feature extraction. Also, I think we have expertise in synthetic data generation, but also we'll be looking for other ways of collecting data and annotating that data. And also potentially video processing aspects. But I think that's it. So we love the team, so I'll be here. Look forward to talking with y'all. Thank you.
Hi, I'm Dave Brady from University of Arizona. We are very experienced in real-time video processing. You go to the next slide. You have a clicker. Oh, I have a clicker. Oh, that makes it easier. Oh, there we go. So we built the gig-pixel cameras for the DARPA Aware program. This is an example of one of those systems. And so our expertise is in data management from very large data sets. This was a streaming 20 frame per second 4 gigapixel camera. At that time, we had rack of computers to do the real-time video processing. Since that time, we've built a infrastructure for managing large video data sources. In our case, we usually do that with actual real-time cameras, but we can use the same software platform to manage video streams from non-collaborative arrays of sensors. And so our main focus is kind of on building the overall data pipeline and how we represent data internally. So to do heterogeneous camera fusion, we built a neural architecture where we extract features, and we're not so much interested in the real ID, the sort of back-end final identification. We're more interested in the internal data structures for real-time video management that can then enable real-time video processing. Here's some examples from some things we've done where we mine heterogeneous camera arrays for underlying features in feature space and then use them to recreate integrated video data scenes. We are doing some work on like hardware-specific video processors for like massive camera arrays, massive video data sources. I don't think that's relevant to this program, but it's kind of a follow-on thing. We're working on both optical and electronic sort of massive real-time video processing hardware. And then we have thought a lot about sort of internal structures, about how to represent data in ways like the transformer networks with Gaussian spotting is an example of a structure that we create where we don't estimate the world. We build a data structure that allows people to extract data. This is a picture that actually is from an array camera of our group. I thought it had like the zoomed in pieces, but it just actually only has the pictures of the group members. But we're very open to teaming with anybody. And again, our focus would be on more like the how you would make very fast, real-time, large data set processors. Thank you.
Right. So hi everyone, my name is Tejas Gokhale. I'm an assistant professor at UMBC, just 15 minutes away from here. I'm going to talk about robust visual understanding in the context of video links. So my lab's focus is twofold. We focus on perception and reasoning and focus on robustness. So for robust image recognition, we've looked at a lot of different types of robustness settings, distribution shift, attribute shifts, and style shifts, and so on. So these are very relevant when we're talking about corruptions or artifacts in video sensors. We've also applied this for overhead image recognition. We've looked at the effects of data augmentation or having multiple data sources when it comes to robustness and how that affects robustness. We've looked at scene completion when you have partial sensor data or when you have missing sensors or compromised sensors. The second focus is on reasoning. Is on reasoning. So we have a lot of expertise in visual reasoning with language, grounding with natural language. And the tasks that we have looked at include visual question answering, video question answering, video captioning, and a lot of other vision language tasks. So particularly, we've looked at robustness from the perspective of foundations of natural language like logic and semantics and spatial features, as well as foundations of vision like 3D geometry, etc. So we use additional knowledge sources and sensors. For example, we've used depth sensors to improve the robustness of multimodal vision language models. So that's one of the ideas that we've brought to the vision language space, to localize objects in relation to other objects by asking and answering questions about objects that you see in images or videos. So in terms of video understanding, we've focused on understanding the effect of actions that objects make. And so here on the top right, I'm showing like a toy setting where the objects are blocks that move, and because they move, they have consequences on other objects. So we want to understand those consequences of those objects in videos through language-based techniques, question answering, captioning, counterfactual reasoning. We've also looked at people-centric video understanding. So this is right in the ballpark for video links, where the focus was to take videos where people are doing actions and go beyond the perceptual aspects of the video and reason about the preconditions for the people doing actions, why they are doing actions, what could be the consequences of those actions. Moving on, recently we've been working on novel concept learning in the context of generative models like text-to-image generative models. So this is different from previous work on novelty detection or anomaly detection, because here the emphasis is to take very small amounts of data of unknown objects, so generic objects as Video Link mentions, and to use those 3 or 4 objects and generate more of those, right? So learn the concept, generate more of those images, and also learn the language or the text or the words, phrases related to those concepts. So even if you don't have annotations, we could have some language embeddings that can help us identify that object again. So especially if there are non-collaborative sensors or compromised malfunctioning sensors, this will allow us to reproduce concepts from different views. So the key capabilities that we are bringing to video links, it's a lot of expertise in visual data engineering, a lot of image augmentation, evolving, learnable augmentation, and novel view synthesis. And this is all, again, grounded in knowledge. The second aspect that is a unique way to look at it. I think natural language is a visual sensor when the language describes images or videos. Essentially, humans describe things. And so those descriptions will allow models to reason beyond pixels to do common sense inferences, which are super crucial when you have different views. So we want to use these inferences to link intelligence from different sensors. And in terms of task expertise, we've done a lot of work on robust image classification, a lot of vision and language alignment, and question answering, video-based reasoning. And so we have that expertise in both the classical image tasks as well as the more, modern vision language tasks. And with that, we focus on building robust models that can adapt and work with limited data. So I've finished right on time, 5 minutes, 0 seconds. Thank you very much.
Our next four presenters are all presenting the remote presenters. The first is Ewing Tai from Dartmouth College.
Okay, hello, I'm Ewing Tai. We are actually a group of professors in Dartmouth College. We have 4 members. I'm Ewing Tai, Yaoting Yang, Soyan Jin, and Yujin Yun. Please go to the next slide. Okay. So some background about ourselves. So I'm an associate professor in Dartmouth College. And before that, I was a senior research director in Quasar Technology in China. It's a company which do the video streaming platform, just like the TikTok. And I'm responsible for the video editing. And we also do work related to video classification and video clustering. And I was also a research director in Tencent, the Tencent is the company making the WeChat, and it do a lot of big game. It's like one of the biggest game company in China. We also do a lot of simulation by that time. I was working in SenseTime, and SenseTime is doing something similar to this project about VID, and I was also associate professor in KAIST. And basically, I have rich experience in both academics and industry. We have good publication in papers related to low-level vision, image or video editing, segmentation, 3D reconstruction, object detection, human pose estimation, and video analysis. You can actually find more information from our homepage and Google Scholar. Please go to the next page. And the second PI, Yaoting Yang, he is assistant professor in Dartmouth College, and he graduated from CMU in 2019, and he has done a postdoc in UC Berkeley. And he's actually expert in machine learning model in how to make the machine learning more general and robust to different environments. And he also published paper related to 3D point cloud object detection, which should be useful in this project. And he's also very good in making the neural network speed up and also using all these different geometric model features for high dimensional space, such as landscape and spectrum density, for improving the neural network. Okay, you can find his information in his homepage and Google Scholar. Please go to the next slide, please. The third PI is Soyan Jin. She was a postdoc in MIT, and she got her PhD in UMass Amherst. She's expert in video understandings, and actually she has experience in object detection, tracking, re-identification, and deep learning. And she has done with her PhD work with a project funded by IARPA. So she has also has experience in this type of project. Okay, please go to the next slide. The final candidate member is Yujin Yun. She is an assistant professor in Dartmouth College. She is expert in graph learning, and basically she can help to improve all this spatial reasoning and address our distribution in the graph learning. Okay, please go to the next slide. Okay, so we are actually looking for teaming with company or other members. Okay, and here is some highlights on what we can contribute in object detection. We have published paper in last year in ICL, which is related to domain adaptation, which try to extend, okay, the generality of the object detection. We have also developed some algorithm which published in last year's CPL on universal object detector, which you don't need to know the object classes, but we try to detect all the objects from image or video automatically. And of course, we have also done some work related to few shot object detection. In tracking, we have done work related to video object and instant object segmentation, which means that we are not only tracking the bounding boxes, but we are trying to segment the region of interest, like in human or car in this project. And of course, we can also track multiple objects together. And we are also developing a very efficient algorithm. And in person identification, we have published paper 2 years ago in TIP about person identification. And we also try to incorporate the multi-view consistent tracking in this person identification problem, which is not only using the feature from the CNN or deep learning, but it also uses the camera information for the consistent tracking. In deep learning, we are expert in spatial reasoning, which try to combine different reasoning in the spatial domain for neural network. And we are also good in multimodality large language model and graph neural network. And finally, we are also good in open set classification, like object or segmentation and open world setting. And also, we are also good in developing long robust feature and uncertain quantification and zero-sort classification. And actually, we are looking for partners like software engineering in company, and we're also looking for partner which can help us to collect the data set, okay? And thank you. If you want to have more communication, please feel free to email us. Okay, thank you.
Next is Jeff Benson of Deja Vu AI.
All right, Jeff Benson here from Deja Vu AI. The thing that sets our software algorithm apart here is the simplicity of our unique computer vision pattern recognition and the subsequent unsupervised detection across a nearly unlimited corpus of imagery data, including video, on a powerful lightweight search engine with extremely high accuracy at scale. So what we do is we take an image using computer vision, search it for a pattern that's found within that image, and match it against whatever the data set available is. And so if that's videos that we're currently trying to do, we're going to search it against video frames, which are just pictures. So on the left is your search engine, and the human brain will see that and recognize the Mona Lisa because our brain is programmed to do that. But most of the image searching out there will try to use different variants and claim semi-sentient AI, but come up without a match. So the Mona Lisa was searched, and using the normally available competitors, we don't get matches because they have a problem recognizing the pattern in it. They see a picture and they're trying to get a like picture. Deja Vu AI will take a pattern in that image and then search it against the data set. Slide. So when you search that, it's matched with a high confidence using that pattern recognition, even despite the variances in the source image, the bad pixelation, the haze, the angle, the rotation, the cropping. So that's something that's unique about what we do in a really lightweight search engine framework. Slide. So the oceans of data available, especially now that we're looking at across video sources, are searchable with Deja Vu autonomously. The input goes, whatever your input picture is, with as little as 1% of an image chip, a pattern can be created and searched against that data set. So from your customer library, you'll get results that come out, give you a confidence rating and tell you, I found this pattern in these pictures or video frames, and it'll show you the overlay with the picture registration against its search. It's a plug-in, pair it with your existing tech. We can help you make sense of your unstructured, unlabeled data so that your analysts can do more with the time that they have. Slide. Search image on the left, pulling that poster out of the back of Seinfeld, searched against the data set. Most of image recognition fails to come up with what that is. And Deja Vu AI will show you exactly what poster that was. Confidence rating, despite the angle that it's at and the scale difference, it's going to show you 92% confident that's the picture that was there. Slide. And that was searched against several episodes of Seinfeld in seconds. So object detection, object tracking. So we're looking at an overhead image of ships in a shipyard. We have the image layout, the ship ID plan, and you'll be able to see on the far right, it's even able to detect minor differences on the component differences aboard the ship's deck. And then using that, taking the corpus of data of overhead imagery, able to follow the asset path, knowing it with a 97% confidence, it's that particular ship in a particular country. I'll dance around that. Slide. All right, because it's pattern recognition, computer vision, we're able to take even really obscure angles on a complex camo pattern and return with high confidence against still images, full motion video, even low quality full motion video, that our search pattern was found in these pictures or these frames of a video across a corpus of data. Slide. So in the support of a human and machine team, we've got a lot of analysts that are trying to locate threats. And they have a database of threats. If they have a new threat, to append that database, they just insert the new threat, search it against the corpus of data, and it'll tell you all of the instances where that threat has been found across that entire visual corpus of data. Threat or slide. All right, here's a unique, this is a SAR example. So using that LiDAR radar cloud, we can take an image of an overhead of Las Vegas and tell you with precision pattern matching what we're looking at. That image on the left, search image goes into there and it says, okay, on the image on the right from overhead imagery, that's where it is. You'll recognize that's the Las Vegas Strip. Next. Search image on the right, top right, that's scraped from Google Street View and put against a YouTube video, full motion video scrape, and it shows with a pattern match, the background of that image was found in the full motion video YouTube channel, despite the differences in the rest of the image.
Next up is Daniel from Reichman University or from Israel.
Thank you. Okay, hi. So my name is Daniel and I'm a computer science MSc graduate from the Hebrew University. Currently, I'm working as an algorithm developer at Elbit Systems. And today with me here is Bar Cohen, which is a machine learning and data science MSc graduate from the Reichman University and is working as a senior data scientist at Siemens. Click, please. In this talk, I'll briefly discuss our joint work in which we developed a method we call Jeff to improve the performance of any close-changing person re-ID model. This work was done under the supervision of Professor Shmuel Peleg and Dr. Ohad Fried. In our work, we present a new term we refer to as gallery enrichment and demonstrate the significant improvement it introduces. So what is gallery enrichment? Click, please. And another one. In the process of re-ID, given a set of labeled samples and an unlabeled query, the goal is to determine the correct identity for the query. In the gallery enrichment process, we suggest to use all the query samples and detect faces where available. Then, based on face recognition, we can automatically label part of the query samples and add them to the gallery, therefore the term enriched gallery. Finally, when applying the re-ID model, there is a greater chance to make a correct prediction as the samples in the gallery are more similar to the samples in the query. Next, I will introduce a recent use case for which we applied our method. Click, please. Okay, so on October 7th, Israel experienced the deadliest terror attack in its history. After raping and torturing hundreds of people, the terrorists left the country in a complete chaos where hundreds of people were considered either missing, kidnapped, or killed. Besides being the deadliest terror attack in the history of Israel, it was probably also the most recorded one. Within hours after the attacks, thousands of videos recording the attacks were discovered. These included videos from security cameras, personal devices of victims, and cameras the attackers carried. As these videos contained vital information to determine the fate of many people, it was crucial to process them as soon as possible. Within this chaos, a civil group opened an emergency center where dozens of volunteers watched hours of mentally unbearable videos. As part of these efforts, many computer vision researchers in Israel gathered in order to automate this Sisyphic work. Bar joined a group of researchers from the Tel Aviv University, and within days, they were able to deploy our method for this use case while achieving the best results of all examined methods. Besides the goal of identifying victims in the videos, the goal of this effort was also to draw connections between the videos, as people which appear in multiple videos can shed more light on which people were kidnapped together and by whom. Click, please. And another one. The developed system was able to connect videos in which the same person appears and build what we called personal files for both victims and terrorists. Each red note in the video represents a video which was caught, and each blue node represents an identified victim. Black nodes are unique unknowns, which means that they are either terrorists or victims that weren't identified at this point. The system we developed showed that it is possible to draw these connections between the videos and is currently being deployed by one of the team members in the Israeli equivalent of IARPA in the IDF. Thank you for your attention.
Thank you. You're sharing my presentation. Can you hear me?
Yes.
Okay, so I'm Mauricio Pamplona, and I'm a faculty at the Department of Computer Science and Engineering at the University of South Florida. And I'm here today representing the computer vision group at USF that has more than 20 years of experience in developing computer vision research. Can you move to the next slide, please? So this slide is just showing, is illustrating like our past experience in different programs and challenges that were carried out by different government agencies, just to show that we have a track record on delivering code, because all of those require delivering code, and some of the times working with some privacy protection, and we have all these environments set up at university so that we can participate in this kind of project. And also these projects and challenges, they involve different areas. They include biometric recognition, remote sensing, activity recognition, and many of those are relevant in the scope of the video links program. Next slide, please. So I would like to highlight some of our past work so you can judge if this is relevant to your team or not. I would also like to say that we are not seeking a prime role in this program. We are focusing on joining a team so that we can use our capabilities to complement and support some proposal and later on working in the project as well. So the first idea here is that we have been lately working on graph analysis on videos. We do perform graph matching between different pairs of images or over frames from the same video over time. And we do have algorithms to work at graph level that not only do the matching between graphs, but also do temporal smoothing, for instance. And we believe that this ability could be welcome into joining videos from different camera feeds to the same geographic space or the same coordinate system, and without when these videos can have like very distinct visual characteristics. Next slide, please. We have also worked in past in video tourism, where we get images from very distinct viewpoints, so not necessarily they are close to each other like you have in a temporal video. So it is not uncommon that you have a wide baseline between the different frames. And we have worked in the past in putting all these different viewpoints together in a same coordinate system that not necessarily aligns with the geographic coordinate system, but this could be something that could be extended so that we can gain this functionality and satisfy the technical area too from this program. Next slide, please. We also have been recently working in the Briar program from IARPA, and we are working on 3D gate analysis and also 2D gate analysis. And we do believe that the 3D modeling that we have been doing from videos can help us understand what is happening over time in one camera and even in multiple cameras. And then this information can also help us joining all these feeds together into a single coordinate system. So all these abilities together could be something that would support the technical area two of the proposal. Next slide, please. And then we do have a lot of experience in biometrics, and this could certainly also help in the technical area one efforts where we need to identify people in the first phase and then other objects in the following phases. And we could help devising discriminative representations of objects in distinct video feeds. Next slide, please. And we do have experience of working with multimodal sensors as well and object detection. Here we have some illustrations of previous projects where we work with different data for remote sensing or for object detection as well. Some of this code is live if you want to check in the European Space Agency's dashboard for COVID analysis. And next slide, please. And we also have some work on activity analysis by mostly looking into people and vehicles. This was done for the active from the NIST active program, but this could be adapted to this program as well. So next slide, please. If you are interested in having us as part of your team, or if you think that our capabilities could complement your needs, please feel free to contact us, and we are going to be more than happy to further discuss this with you.